In this video, we're going to be talking about deposition and lithification of cement to make sedimentary rock.
Sedimentary rocks. Sedimentary rocks are any of those rocks that are basically composed of other types of rocks that have been transported in some way and then redeposited. Here behind me you can see that the various sedimentary rocks are unusual compared to metamorphic and igneous rocks in that they are deposited in layers. These layers are called bedding. And you can see a bunch of stacks of layers behind me. Those are layers of rocks that have been deposited, transported mostly by rivers, sometimes lakes, sometimes sand dunes, any sort of transportation of those bits and fragments of other types of rocks.
Hey, what do you know? Utah is figured in our textbook. This is Capitol Reef, and you've probably seen a lot of figures of sedimentary rock in Utah. This is what gives the characteristic banding that we see in the sedimentary rock. And that's because sediment is laid down in layers, and that layers basically, as it's deposited over time, changes depending on what's happening in the world. So as climate changes, or maybe the depositional source will change, or maybe it becomes uplifted and starts to erode a little bit, all of that's going to produce a banding appearance that you see in sedimentary rocks. We refer to this banding appearance as bedding. So bedding is this patterns of different layers of sediment being laid up over time in a particular area. Now there is a process of lithification that involves three important steps. So the first step is that the sediment, as it accumulates in an area, it's going to be buried. And as it's buried over time, it's going to undergo compaction. It's going to compact all of those grains together, such that the spaces, the pore spaces in between the sediment are going to be pushed together. And so there won't be as much pore spaces between the various grains. They'll be crushed together and squeezed together. The next part of our lithification of turning sediment into rock is to take cement and add some cement in here. The cement will cause the particles to adhere to each other and sort of glue together. So we've got to add some glue to our rock here. Dump some of that in there. All right. And some of the types of glues that are used in making sedimentary rocks to glue them together, the cementation of rocks, include things like calcite and quartz, as well as hematite. These are found in nature, and they basically get carried by groundwater. Quartz, when the groundwater is very hot, so groundwater mixed with quartz will cause glue to form, act as a great cement. Calcite usually does it at room temperature. In fact, if you have a little bit of that carbonic acid, you can dissolve calcite, and that can seep down in between the grains here and start the lithification process. The third process of our process here is to have some recrystallization. And that's where the grains get squeezed together so tightly that the edges of them start to form some recrystallization, often growing little halos being squished into various areas. Especially if you have a lot of quartz, you may get recrystallization of quartz between the various grains. Now those occur at low temperatures and low pressures relative to some of the other rocks we're going to be talking about through the rock cycle. We refer to this lithification process and the stages of the lithification process as diagenesis. So the study of the rock's diagenesis will tell you the processes that created that rock. This is an excellent figure from your textbook showing the three steps: compaction, cementation, and recrystallization to form sedimentary rocks out of loose sediment. So what are some of the characteristics of sedimentary rock that will help you identify sedimentary rock when you encounter it? Well, sedimentary rock is the only rock that has fossils. So if you find fossils in a rock, you know it's going to be sedimentary. The other thing to look for is rounded clasts. This is sediment that's been transported, and as such, it should have some rounding of the various clasts that are in the sedimentary rock. Sometimes breakage, some sort of little bit of rounding. When you look at igneous rocks, the minerals that are in the igneous rock are all kind of crystallized together. So they're crystals that have grown into each other. When you look at sedimentary rocks, they will be sort of surrounded by some sort of cement. And that's the best way to identify sedimentary rocks from igneous or metamorphic rocks that we'll talk about later.
All right, I mentioned that sedimentary rocks have fossils in them, and I wanted to show you that to you. If we look right over here, we have a fossil here in this brown sandstone. You can see this round part here. This is a bone that's part of the scapula, the shoulder part of an ancient mammal that lived here about 46 million years ago, belonging to a group called the Perissodactyls. It's probably a brontotherium. We can see another bone here in this sedimentary rock. This is an astragalus. This is one of the ankle bones. Probably belongs to the same creature. Sedimentary rocks are great places to look for fossils because igneous rocks are melted, and they destroy any fossils, any remnants of ancient life. And metamorphic rocks are buried really deep under intense pressure and temperature, and so fossils get destroyed that way. So sedimentary rocks are great places to find fossils, the only of the 3 types of rocks that you do find fossils in.
So let's talk about names of sedimentary rocks, and we already touched upon this in the previous video. So with clastic sediment, when it gets lithified, the name corresponds to the size and characteristic of the clasts, the grains that are inside the rock, such that large grains will be called conglomerates. If they're extremely angular, we call that a breccia. If they are between about 0.5 and 2 millimeters across, we call that a sandstone. So if we grind this up in a mortar here, we'll produce sand from sandstone. Same as true with siltstone and mudstone and claystone. Shale is mostly clay-sized particles in a rock that split very easily. Here's an example of some shale. It will split easily across these planes here. Now, I want to share some exciting news. This is a photograph that was taken by Curiosity, the rover up on Mars, recently. And take a look at this rock. This is a sedimentary rock. Note how the various clasts are sort of rounded, much like our friend Charles here, and they have a certain features to them that they were transported sediment before they became lithified. This is the strongest evidence that we have of liquid water once on the surface of Mars. There are other types of sedimentary rocks. The chemical sedimentary rocks. Chemical sedimentary rocks result from the lithification by chemical sediments that we talked about previously. So for example, salt can form evaporitic rocks, such that you might find around the Great Salt Lake. We also have banded iron formation. These are actually really kind of exciting. These banded iron formations are not found here in Utah. You have to go to the centers of the cratons of the North American continent, places like Michigan and up into Canada. Banded iron formations were deposited during an interesting period in Earth's history when there was very little oxygen in the atmosphere and the ocean, such that iron precipitated out of the ocean water. This laid down layers of iron oxide, such as hematite. These layers are deposited in sort of these bands, and so it's referred to as a banded iron formation, or a BIF, as it's often abbreviated. Banded iron formations are important areas for commercial mining for iron. Limestones are basically where you take lithified shales and other skeletal material, usually composed out of calcium carbonate, and that is glued together, oftentimes with a lot of calcite, and forms limestones. Chert, as your textbook kind of references, is basically caused by a number of other organisms, usually things like diatoms that actually have quartz or siliceous skeletons that they produce rather than calcium carbonate. These can add quartz into sedimentary rocks, which then become mobile. A lot of chert is also produced if the rock during the lithification process was under high temperatures with a lot of groundwater flowing through, enough to melt the quartz but not the surrounding rock, thus carrying the quartz and depositing it in cavities or pore spaces that exist within the rock. One of the most extraordinary things about sedimentary rocks are its bedding and the stratification that results from the variety of different layers being deposited over time.
I'm here in the Bridger Basin in southwest Wyoming, just across the border from Utah, and it's one of my favorite sedimentary rock layers, and it's a great place to tell you a little bit about Nicholas Steno's 3 principles of stratigraphy. Nicholas Steno came up with these ideas in 1669. The idea was that there were 3 principles in which dictated how sediment is deposited down. The first principle is the law of original horizontality. And that means if you look at the rocks behind me, and as we pan around and look at the rock layers, you'll note that they're originally going to be laid down horizontally. Any of the tilting that you see was going to be created after deposition. The second principle of Nicholas Steno was that the layers of rock at the bottom are going to be the oldest, while the layers of rock at the top are going to be the youngest. And this is called the law of superposition. The third law of Nicholas Steno's is that there is a lateral continuity of rock layers. So as sediment is deposited, it's going to be spread out over a lateral distribution. And then as you move across and pan around and look at the rock layers, you can see that they sort of have a lateral distribution across the landscape. These 3 principles, Nicholas Steno said, were kind of obvious laws. However, they're very important because they set up the idea that any tilting or faulting that you see in rock layers occurred after they were deposited. So I'm here in the Bridger Formation, and just want to show you how rich this formation is in terms of fossils. This is a Eocene formation, and you can see I got right here in my hand, this is probably a metacarpal, one of the toe bones. You can see the articulation there, but if you look, you can see all this stuff. I got some ribs here, and you just look at it at the ground and it's just covered in bones. So one of the things I look for are fossil teeth, and I just found a tooth here. This is part of a tooth, a part of the upper premolar, looks like a paracedactyl of some sort, but these are nice because you can identify them down to species.
Sedimentary rocks, because they are stacked over time, can tell us a great deal about the history of the Earth system. They record the record of Earth's history in the various layers that are laid down through time.
So the law of superposition is one of the more important of the 3 laws that Steno came up with. And if you look behind me, we have a package of sedimentary rocks. They're stacked up in layers. And what the law of superposition basically states is that the bottommost layer that's down here is going to be the oldest, and the youngest, which are up here, are going to be the youngest of the layers.
One of the things we can also do with these sedimentary layers of sedimentary rock that's been stacked up over time is we can do what's called stratigraphic correlation. That's where we compare one set of beds to another set of beds and can correlate the two, such that we can see if deposition was much more prevalent in location A compared to location B. We can also map out stratigraphic beds to see where they lie in the surface of the Earth, as well as in the subsurface. This is extremely important in terms of mining and petroleum exploration. Once the sedimentary beds are laid down horizontally, they can be tilted, uplift, and deformed depending on the tectonic processes that are working on the Earth's surface, such that when you have mountain building events, such as isostatic rebound, these beds can be folded, tilted, and upturned. One of the other things that can happen with these sedimentary layers is you can get periods of time in which the sediment that was being deposited gets interrupted or was not laid down. We refer to a sequence of strata of sediment that's being laid down during deposition without any interruptions as being conformable. When there's breaks in the sedimentary layers that represent missing bits and pieces of time, such as non-deposition or maybe erosion, we call that unconformity. So an unconformity is a break in the strata. There are three important types of unconformities. The first is a non-conformity. A non-conformity is basically where you have very old igneous or metamorphic rock below, and then you get a record of sedimentary rock on top of that old igneous or metamorphic rock, such that there is a period of time in which that rock was exposed to the surface, but deposition did not occur. The next type is angular unconformities. Angular unconformities are the easiest to recognize in the field, and that is where you have the beds tilted up, and then erosion happened to relay down a new layer that's then horizontal. So, for example, here in 2, where you have beds that have been tilted up and then eroded with a new set on top of that. The third type is what's referred to as a disconformity, often also referred to as a paraconformity. This is basically where you have a surface of erosion that's parallel to the bedding plane. One of the other really important principles is the principle of cross-cutting relationships. This is going to allow you to date various layers of sedimentary rocks. Now, since sedimentary rocks are never molten, never a liquid, they remain a solid, we can't use radiometric dating on sedimentary rocks. However, we can use a number of other tools. One of them is using the cross-cutting relationships. For example, in this figure from your textbook, where you have an intrusive igneous body that was molten and cooled 34 million years ago. We can date that igneous rock, and it will have a date of 34 million years. We then know that it must have occurred there when layers 1, 2, and 3 were being deposited, because it had to have a rock to flow through for it to be there. But we know that layer 4 occurred after the cooling of the igneous rock body B 34 million years ago. If we have another set of cross-cutting, like a lava flow that comes through for a conduit for lava that cuts through 4, we know that the layer number 4 is between 20 million years old and 34 million years old because of the principle of cross-cutting relationships. One of the most important things about sedimentary rocks is that they preserve a record of the Earth's past. They're important for preserving fossils, and so they give us a picture of the immense history of Earth. So if you want to reconstruct what the environment was like 10,000, 100,000, or 100 million years ago, you can use these sedimentary layers that are laid down. Thus, sedimentary rocks are an extremely valuable source of information in the Earth system sciences because it tells us a record of the various processes that have worked throughout the geological record on Earth, and give us a picture of times in which the world was remarkably different than it is today. So that completes our video on sedimentary rocks. In the next video, we will talk about metamorphizing our rock. So here's Charles. He's now a sedimentary rock and a very nice conglomerate as well.